take a derivative. Because otherwise, this is a piecewise linear function. I'm worried about corners. And so the uniqueness allows me to say, well, it's linear, so it's smooth. Yep.
I'm so confused on the A equals A of theta star. Isn't A constant?
No, it depends on theta. You take a look right there. It depends on theta to the policy. So this is going to be some, without the expectation, this will be some piecewise linear, even discontinuous function.
You got theta star on the outside and the inside.
Well, no, but that's what's so awesome is there's a free lunch. So you can estimate this online. Just go do it.
Shove in whatever theta you have so far.
Yeah, an average. It works.
And then just keep going until you get it.
It's a free lunch theorem. It really works. It's really cool, you know.
You use successive approximation.
Yeah, but you just go and average this monster. So basically, yes, in practice you don't know theta star, but you know that your estimates are converging to theta star, and you just plug in theta n and average these observations. And so you can actually estimate to see if your variance is infinity. And it also tells you how you maybe, if you have a scalar gain, it tells you how you should ramp up that gain to make sure your eigenvalues, resulting eigenvalues satisfy this bound.
This only works because it's discrete, right? If you work in teams,
Well,
and what's the meaning of like
yeah. But all of this, but it's a finite-dimensional parameterization. X, no, not at all. Take a look. X there's nothing here from stopping us from taking X to be the belief state and YT.
That's fine. But I'm just looking at the bottom equation.
Where? Yeah, theta is an RD.
Theta star equals A versus theta star times B.
It is just a D by D matrix. See?
It's D by D because this is a discrete system.
No. It's D by D because of our choice of basis. We're right there. X can be in some infinite dimensional manifold. It doesn't matter, you know. Yeah. I'm really crucially using the U is discrete in my arguments here, but even that could be relaxed. Yeah.
The only thing that's finite is how many thetas and dissociated.
Theta is in a finite dimensional space.
One thing that
It's an RD.
is also,
Yeah.
when the theta was inside, that was a dot product, so you would just get a scalar out of it, right?
It is still a scalar. This times this is a scalar.
But now if you take the expectation of dot, you get like a vector of values that would multiply with the other thing would give you a scalar.
Well, this whole thing was a d-dimensional equation, you know. So because the thing in brackets is scalar, and that is a vector, a d-dimensional vector. And so I moved it to the left-hand side just so I could get something times something transpose.
What's the size of A?
D by D.
D by D.
If theta is an RD. And that's because this is a d-dimensional column vector, and psi is a d-dimensional column vector, but I'm taking a transpose, you know. And this thing here I'm just evaluating, so that's a d-dimensional column vector as well. So I take the difference of d-dimensional column vectors here, take the transpose. So inside there's an outer product, but then I take the expectation.
You take the expectation out, so
Yeah, and so I'm taking a convex combination.
Of each index in that.
Yeah, that's right.
So
Yeah, that's okay. Yeah. And so, so you can, it's not a big deal to go and estimate this just as you go along. Yeah.
So this is the same as Q-learning, just in like a matrix form, right?
This is Q-learning. This is a goal of Q-learning. Well, this is not Q-learning. This is the goal of Q-learning to solve these equations. The algorithm. The algorithm is your choice of this eligibility vector.
You just run the iteration to the bottom equation.
Yeah.
You
Where?
pick theta, you plug it into A,
Yes.
you invert it,
Yeah.
you multiply it times B, you get a new theta, then you plug it back in.
And this
it's
should
just
be
so on and
exactly
so
the same as what we're doing.
No. Oh my God, be careful. Oh no, be careful. Now, what you're describing is something really cool, and the successive approximation is not. So what we've defined as Q-learning is you just take this, you do this stupid successive approximation, right?
Yeah, we like say like we move theta
Can I-
in the direction of.
Can I kill this now? I mean, how we've defined, our Q-learning has been theta n plus 1 equals theta n plus alpha n plus 1 times that, what we call, well, forget the f bar, f of theta n phi n plus 1, say, where phi is everything. You know, phi is that and that and that. You know. What would it be? It would be xn, un, zeta n, and xn plus 1. You know, all the random stuff, just throw it in to form one giant Markov chain.
The other way, though.
What?
Wouldn't converge?
For what? Do what? No, but the thing is that compute this for all theta, you'd have to do independent runs for every theta. You know? You'd have to fix a theta, run this for a million samples. Another theta, run it a million samples.
Until you get converged on each
Well,
theta.
no, but you don't know which way to even start. You know, you have a grid of RD, you know, you couldn't do that. We need one recursive algorithm. Trying to compute this for every theta would be just a nightmare.
Why are you over there writing, you're going to call that Watkins algorithm? The thing we talked about.
Yeah, Watkins, what is Watkins? Watkins has two components. One, lambda equals 0. It never even, I don't think, wait, no, but he said maybe he did mention lambda non-zero. Or, anyway, but the way people define it, lambda equals 0, number one. Number two is that the psi I of x u is just, it's equal to the indicator function that x equals xi, u equals ui, an enumeration of all that. That's two. And three, I'm sorry, I beg to differ. Most people, when they introduce this algorithm, take alpha n equals 1 over n. Now, I'm told by Aditya that some people would scream at me that they put a constant in front. I think in most books they take g equals 1, but okay. All right. Yeah, and if g is small, the covariance will be infinity. For g large enough, the asymptotic covariance will be finite.
What is the name I can use to refer to this algorithm without those constraints?
Well,
It's general.
we're going to call it q of lambda. We're going to make up that term. Q of lambda learning. Yeah.
Q of lambda learning.
Essentially, Watkins would look very similar here, but instead of having the zeta n term, we would have just like
Yeah.
a phi of xn minus 1.
You just replace this with this. Watkins takes this equals this. They're the same. No, don't, let's not, it's complicated to write down. You have to have an enumeration of all states. You know what I mean? I can't make this any simpler. I can't write this any simpler. This is going to be a gigantic column vector, you know?
That's fine. That's
Yeah,
fine. I'm just
no.
saying like the zeta just becomes, because we wrote an equation that says zeta n plus 1 equals lambda times.
That's what I just was saying. This is this. See? Yeah, that's all I'm saying. Okay?
But with the Watkins, lambda is 0.
Yeah.
So
That's what I mean. If lambda equals 0, then that is equal to that. They're the same thing. Right?
So I followed that pretty well, thank you. So A is unique.
Well, yeah, I mean,
And we're using, let's say, A hat to approximate A.
A is unique. And then, we're going to, I mean, so I guess we can kill this now. So, well, no, well, I mean, what one would do is, I wish I'd colored chalk. I would take, I would define, in practice, I would define A n plus 1 to be that with the last parameter.
Yeah.
And I guess I have to write it down. I mean, it's...
So you could just write it there at the bottom in the box, but just put a hat instead of like the star.
Yeah, but I think that I'm worried that some people won't know what I mean. So I think I have to write it down.
This is the
Got that minus. Okay, so the big difference, put it in bold chalk, is I'm going to plug in theta n because I believe my theta n's are convergent to theta star. And then I would define a hat n to be the sum t equals 0 to n minus 1, say, of a n. You know, and so the thing is, you know, initially your guys are off, but you're dividing by capital 1 over n. But you're dividing by 1 over n, so you'll throw those guys away anyway. Yeah. So if the estimates are converging, this will be consistent. That will go to theta 8. It then goes to infinity.
That will go to A of
Theta star.
theta star.
Yeah. If theta n is if those conditions are met, first theta n converges to theta star, and this uniqueness condition I gave you. Those only just those two conditions.
So you don't need, you still need like an update for theta.
No. Remember, this is you're running the algorithm. I couldn't. Those theta n's are right there.
But that one?
Yeah.
That's like the one on the bottom.
Well, no, there is no other algorithm. That's not an algorithm. You can't compute this. You can't approximate this for every theta. This is really useful. So that's the trouble. You couldn't compute A of theta for every theta in RD.
Okay, so
Yeah.
so you couldn't compute that B sub theta.
That's a damn problem. The fact this weird nonlinearity here. If it wasn't for that, you could just compute it. If this, you know, if this wasn't there, you know, yeah, and yeah, I mean, there's only a finite number of policies if you have a discrete action space and state space, so you could compute it for every policy. You could do that, but there's a lot of policies. It'd have to be a very small state space and action space. Yeah.
Even if we assume that our theta right now is theta star, and then when we plugged it into A inverse, we carried out that phi of a psi of xn plus 1, you know, comma b sub theta, like the nonlinear.
Well, there'd be a data storing problem. You'd have to store all your xn's up till. So if you run this for 1,000,000 samples, and it's I know what theta star is, and then go through and try to estimate this with that fixed policy, it means you've stored all of your observations up till now. I'm not sure. I mean, it's something you could try, you know, but I don't know if it'd be a lot of data to store. You have to wait until you learn theta.
Right there, if we plugged in the theta that we currently had,
Yeah.
and just use that, like, we wouldn't be able to run like a successive approximation on the thing in the box in the middle.
Now, if you know theta star, then yeah, you can do this. Just fix and run.
The question is, given a theta, why can we not just evaluate that?
You can, but you don't know what theta to run until you run some algorithm like that. You have to learn there's some mechanism to learn theta. Now, if you don't have this running, you'll have to estimate this for every theta.
Well, but I think that what he's saying is you choose your thetas by iterating on that equation.
Yeah,
You're not doing it.
I don't know how to do that.
I think the expectation is
Well,
You need more than these.
but yeah.
Iterating on this equation is really similar to iterating this. I don't know how.
Okay, so you're saying the problem is in calculating the expectation.
What we're saying is just plug in a theta for the expectation,
Yeah,
like zeta and as that line right there.
but how would you compute this expectation?
To calculate the expectation.
You'd have to do it Monte
That's
Carlo.
why he has like the
Yes.
Right.
Yeah.
If you're going to estimate this expectation in Monte Carlo, you'd have to fix theta and then run up to say 1,000,000 samples, or 10,000 samples, without one theta. And you would just learn native theta for one theta, you know, and then you have to do that over and over again. You know?
So why don't we have to do that with the?
Yeah, because if this is designed so it's convergent, then you go through
So
and
it's like a stack of thetas right there, right?
yeah, there's an iteration here. No, I mean, this is a beautiful thing. You notice that well, here I kept theta n. So given my previous estimate theta n, I have two updates. I update to get my theta n plus 1, and I update to get my a n plus 1. You know, and I can do this recursively, estimate, you know, come up with these
What's the
estimates.
size of theta n plus 1?
They're all d-dimensional vectors.
That's what I meant.
Yes, yes,
So
you
they're
update
all
all
updated all at
these.
once.
Yes.
That's what I mean.
Is this recursive? Every time step I update my thetas, I update my A, and then I update my AM.
So I just noticed this, why is there no expectation on that A update equation?
This is just the thing I want to average. This is approximately thing within the expectation.
Okay.
And the average there is approximating the
That's why you don't have
expectation.
to do it above
Yeah.
1,000,000 times for everything.
So
Yeah.
we would do all this so that then we can just when we feel theta has converged, we can just assume that we have A and do this
And do this
check right
test?
there?
Well, shall we? What can we do with this beautiful thing?
What was the question?
I was asking if we're computing A, because ultimately we want to theta. Like, I don't even see where A comes.
All right.
This average A will like converge to A of whatever, like it's a weird like slew of thetas.
No, but this works. So fuck that. this works. If that algorithm converges, to theta star,
Yeah.
then running this in parallel, this will converge to A of theta star.
But all this stuff at the beginning when data was very far from theta
Doesn't it get
star,
thrown away because of the 1 over n? It does. I mean, it's just wonderful.
Yeah,
It's a wonderful world.
So what we could do is we could run this until we see, the data
Yeah.
start tapering off, and then we could start our
Yeah, well, yeah. I mean, sort of, but you don't know when to stop. There's better things to do. There's things that are easier to do and might be faster. I'll explain. Yeah.
In the alpha n plus 1 times F, would A n there go somewhere in there?
No.
It's F.
Well, we will talk about that, but for now, let's say you're doing your favorite Q lambda algorithm, and that's what that is, so that's your favorite Q lambda algorithm, and alpha n could be G over n, say, and while you're running, so one thing you could do is just a reality check. As you run this algorithm, you go in and compute this, and you do the eigenvalue test just for reality test. Is my algorithm stupid? If you find one of the eigenvalues is minus 0.003, as it will be for if you take the gain too small, then you're screwing up. You've got to crank up your
So we
gain.
can use this, run our algorithm, and use that A that we
Yeah, very hard.
central limit theorem towards, or what is it, law of large numbers.
Well, it's a central. that's a law of large numbers. Yeah.
And we'll use that to say okay, now basically that A has converged to A of the final theta that we guessed, and we're claiming that final theta is theta star. So now we're going to look at the properties of that A matrix to determine if our algorithm was even.
Yeah, and if you find that it has an eigenvalue that's really close to 0, where that test fails, then you've got to take the Jonathan Brooks test and do a lot of runs, because you screw. The variance is infinite, so you can't trust your estimates at all.
Yeah. I mean, if you run 2 times in a row and your thetas are within 2% of each other, then you're probably.
Well, yeah, but only under the JB approach. You have to take a lot of runs very far apart.
I think what he's saying is the thetas might actually get close to each other and your n might be crap, so
Yeah.
you're asking
That was the example I gave last time, where everything looked really good, but they were all bad. And it's because all of them were initialized near the same point. I mean.
Wait, we should have different points for initializing thetas?
No, well, that was the fix number 2 or something. I don't know. Fix number 1. Yeah, fix number 1 was given right here. No, but let me go back. I want to keep that. I'm going to erase this unless it's a question. I'm going to. Yep.
So, general
Yeah.
question about this. So we looked at optimizing the covariance. We said the optimal gain was a negative A inverse.
Yep.
And then, so what I'm confused about is then, but it's possible that A has eigenvalues that don't meet that criteria.
Yep.
So does that?
I'm about to answer this question.
Okay.
Yeah, that's what I'm waiting to say. Yeah. No, I mean all that about how you would use the knowledge, all that knowledge to improve the algorithm is my next step. But I want to answer this question first. I mean, but I can erase this part. I'm going to keep that. I mean, just for the sake of example, let's just take an example that I saw this morning. Okay, and this, say is 11, and that's 0, and that's n. you know, and you say, fuck it, I did it. And you say, puede again. Sorry.
What's for alpha? What would the alpha?
No, I'm just saying, suppose you saw that. At the very least you should do is try another run way above, you know, at the very least, you know. So this is like the first guy. And this is very likely to happen, you know. So just do 2 runs. The fifth entry, because theta is a vector. I mean, I have to talk about entries. I can't plot it. Yeah, that's the 5th entry.
Okay,
yeah.
But you also had the 1 and 2, so I was confused.
Oh no, this is the first. I do my first run, and I go like this, and I say, yes, I did it. I've converged. You know. I said, my God, it's 1 million samples. It's still constant. I've converged. Well, I'll tell you, you can go to 1 billion samples with the simple Watkins algorithm on a 4-state 2-action model, and you won't see anything. I mean, it can be that bad. So at the very least, try something way on the other side. You know.
What do you do if you see that though?
That's the thing. That's why it's important to know A, because then you know there's a potential. If the eigenvalues violate that condition, it's really likely you've got a problem. You know, but so Johnson's idea was to, when we do these histograms, we should initialize just randomly the initial theta zeros over a very, very large region. It's a uniform of a gigantic region. But at the very least, do 2 runs and see if this happens. You know.
Okay.
Yeah.
What do you mean by the other side? Or how is it that those
Right.
shift in space?
Well, here, you know, it looks so good. You know, I have this overshoot and I converge. So, you know.
We gotta give it a value initially.
Yeah.
Okay.
So at least I try maybe.
Yeah, that's a different initialization.
Yeah, and then you know, well, the variance is very, very large.
So if we see that, then that means our A is correct. Yeah.
Well, yeah, that's right. And so what I want to do before we still got lots of time. So I want to show you how you can fix that. Yep.
Oh, well, maybe you just answered it, but I was going to ask if you do get an A with infinite variance, or with a real eigenvalue of about -1/2, then how do you, and say you do all these initial condition tests, how do you know which ones?
They're all bad.
They're all bad.
Oh, they're all bad. There's nothing. If you don't have a histogram.
So there's no reason then to even do a bunch of different tests. There's no reason to do the JB algorithm at that point, because you're not going to know which one's real.
Well, they're all crap.
So if you pick 2, what you're saying is like, if we do
Yeah.
2, just 2 runs, and we already see that they're not convergent to the same thing for each individual theta,
Yeah.
then that means our A is bad.
Yeah.
Which means, from looking at A, that we picked the wrong basis.
Yeah.
Because that's the only thing we have to do.
Oh no, we can like I said, that alpha, like one thing we can do is alpha n equals some constant over n. If G is big enough, it's going to work. Well,
G's too big, it's not going to work.
well, the variance will get high. You're right. I mean, if G is too big, it won't work. But if G is big enough, we won't have that problem. We have different problems. You're right. I mean, yeah. Forget it. Let's not. You're right. But I mean, but G, this problem, that's what I'm trying to get to. Exactly. That's what I'm trying to get to.
What if you just like computed an A hat on the spot?
Okay, you give the lecture. That's what I'm getting at. Yeah, that's what I'm getting. And the thing is that all of these questions are really good because you point out to the flaws in this. So, you know, if I'm claiming that, I say, if it converges, then this is true. And that's true even if this is infinite variance. The trouble is that you'll have to wait billions of samples for this to be good. So there is some kind of real problems in the theory. There really are gaps in the theory. But you can forget that and try it out anyway. Pretend this is a good estimate and use it. And like what you say, use it for that purpose. All right? And let me give some examples. There's a million ways you can use this information online to change the gain as you suggest. Right? So you could do this. So one is something like you said. You take your A hat n, And I have to put in a little n there because I'm going to do this all recursively, you know what I mean? At every stage I've got this, I can update this. I mean, I wish, I don't know why I put a capital N there. Oh, look, there's a typo anyway. Hey, everybody. T was a sum there. And if T is a sum there, I wish I'd made all those little n's. If I could make all these little n's. And then it's clear that it's all recursive. Okay, so I could do this, maybe not every instant, maybe do it every 100 steps or something. You know what I mean? Every 1,000 steps, I don't know. But just look at the eigenvalues of A, and what you're going to find is you're going to get something like this. This looks really complicated, but you just find some way to do this approximately or whatever. And I'm assuming the one that's closest to my danger region so there's 3 eigenvalues here that violate my constraint, all right? And that, it looks like I've got one that's at a quarter, let's say. So there's the worst one, that's called lambda 1, say. So I got one nasty eigenvalue. So what would you do if you wanted your iterative thing? And these depend on n. I mean, I don't want to have to do it. I'll do it if you want. These are the eigenvalues. So the D eigenvalues, some of them will be complex in general. And there's going to be one that's closest, whose real part is closest to the imaginary axis. So what would you do?
Multiply G by 4.
No. That'll kill you. You're close. Well, the thing is, don't forget that. Don't forget that the condition. If I have an equality, I'm still screwed. So if this was actually on this line, minus a half, the asymptotic covariance would still be infinity. So you got to make it a little bit bigger.
4.1.
Yeah, 4.1. So I'll take Gn to be 1.1, say. How about that? Divided by lambda 1n. A little different than what you said. 10% bigger. How's that? And this is real, of course. And oh, yeah, absolute values. That's negative, so just have to make it positive. All right? All right. I can, if you look at the handout where there was one scalar gain algorithm, something similar to this was done, really. I mean, not exactly, but similar to this. All right? And it just was amazing in that example. So in that example, which was that pathfinding problem, all the eigenvalues were real and very close to each other. So it was easy just to move them all and be okay. Where you really get screwed is if this is practically at the origin. Right? You've got one that's almost on the imaginary axis, and others that are out here. And G is 1,000, and it's great you move this guy out here. The other one's got mapped out to way out there, and you get just a miserable mess. And that's when you really would rather have a matrix gain algorithm. You want to be able to condition the thing. Either change the problem somehow to make it better conditioned, or introduce a matrix gain. What's that?
Like the Rover problem, what kind of eigenvalues is good enough to write?
Well, it depends on your algorithm. Yeah, well, that's why I asked you for your. I asked you for your theta, your psi transpose mean. I sent you an email about, well, that's another point I wanted to make. There's so many things about design I wanted to talk about. Remind me to say something else. That's one thing you can do. Another thing that I've always loved, and now I don't think it's maybe the best approach, is it's something I always called stochastic Newton-Raphson. So if you look, none of you have done it, but if you had read the stochastic approximation notes, you'd see that I whine about why doesn't anybody use, why is the term stochastic Newton-Raphson never used?
really understands the wacky subgradient arguments.
No, but just in general, I mean, you can. This is just for Q-learning, but in general, you can estimate the gradient of f, and just use the damn thing. I mean, why people are scaredy cats or whatever. I mean, and what you do then is you take alpha n, you take a matrix gain. You know, I'm just going to write an arrow and going to get rid of that. So I'm going to take this gain and replace it by, instead of a scalar, a matrix gain, and I'll make it 1 over n plus 1 times a hat n plus 1, what the hell, all inversed. You know, and if it's stable, it's optimal. So, I mean, if it's convergent, it's optimal. You know, and the thing is that in the condition I mentioned, if this is really a condition, this could be a monster. And so you know, let's be careful. So maybe don't do exactly this, condition it a bit. Don't do exactly this, but something, you know.
Use like G until, you know, you run it for a little bit.
Yeah, well, that's another thing. It's a good idea to, you know. But in either case, you'll probably, in many cases, you'll probably need projection. Probably. What I mean by that is it's just because if this gain is going to 0, whether it's matrix or whatever, and if theta n suddenly hits 10 to the 4, then this will stabilize you, but it could take forever. So, you know, when you have a bad event, it takes forever to recover. And so if you know the parameters, it's ridiculous that they could be 10 to the 10th. You just pick some ball and you make sure they don't get there, and you won't have transient problems and all that. All right, so that's something that's never failed me. All the examples I ever looked at, it's incredible. It's just absolutely incredible. Yeah.
Well, so
Yeah.
So it's optimal, you know, if we converge, because are you trying to say that gain is not going to let it settle if it's not correct?
Let's say it again.
Like does doing this A inverse approximation, guarantee our end result is going to be correct in the sense that it won't let it settle until it's at the right data value?
Well, remember a very cautious statement. If theta n converges to theta star with this algorithm,
Theta star, okay.
Yeah,
not just converges in general.
But you can, if this converges, the limit has to be. Oh, wait a second. Yeah. I mean,
it seems too powerful if it's just like, oh, it's settled and I'm using this thing and I must be right.
Well,
It has to be because that is 0.
Yeah, that's the thing. Is if theta converges to anything, and unfortunately with this algorithm, if the phi theta is unique, because otherwise there's some discontinuities here that would persist in the limit, which would scare me, you know. Then theta goes to theta star. The discontinuities here, the fact that there's a discontinuity there, if theta was converging to a limit in which my uniqueness condition failed, I'd have trouble analyzing it, you know. And that we're in no man's land then. I don't know. Nobody does. It's not. It's a lot of this is uncharted territory. But this is kicks ass. In all the examples I ever looked at, this is what I've done, and it's beautiful.
Why did you cross out that alpha n plus 1?
I said, forget the scalar gain. Try this adaptive matrix gain. Yeah, I just didn't. That was a scalar. It just felt like an abusive notation.
And what does you mean by probably need projection?
Well, for here, if I try to, if these guys aren't, I mean, in this case where seems like they're all really close to each other, I might not, because when I move that outside of the -1/2, that doesn't move very far, you know. But if there's a bigger spread, I could see a lot of transients in the behavior, and I might have to project whenever theta any entry is outside of say some region, I will push it back in. If it's ever bigger than 1,000, I'll push it back to 1,000.
That's different from using a matrix.
No, that's different. On top of that, I'm throwing a projection to avoid weird transient behavior. That's the thing. The asymptotic covariance is an asymptotic thing, and it's a beautiful object, but transients matter too, and projections are to deal with the transients. Yeah.
But these are more or less just hacks, right? There's no theory.
Oh,
thing.
this beautiful. Well, this is almost perfect.
It'll still converge even though you're...
Oh, yeah. So the original, oh, yeah. If the original thing converges, a slowly varying positive gain will still converge. That's the wonderful thing. The convergence theory is insanely robust. You know, I mean, this thing, I don't need any conditions on alpha except for what I told you, that it sums to infinity and
what if
yeah.
Your adaptive gain ends up being, you know, your real part of lambda is going towards 0.
Yeah, well, I won't let it. I won't let it. I'll project that between some bounds. Yeah, that's right. I will hack that, but it will work.
Okay.
You know, I mean, that will work.
Okay.
If I don't, you know, let that happen, if I make sure that I keep, where is it? If I do, all right. You know, I mean.
G is bounded.
How about that? just do some hack to make it bound. The theory is crisp. It will just work. You know, you'll get exactly the asymptotic covariance you expected. It will, if it converged with a constant G, it will still converge with this, and you'll get the exact asymptotic covariance you expect. Yeah, but the theory is, the only reason the theory is difficult is again because this is a discontinuous function of theta, and so the ODE methods you use are difficult to apply, you know, for Q-learning. You know, next week that'll be clearer. We're going to talk about the ODE method, and you'll see that we assume up front that our right-hand side of our differential equation is continuous, and so we need to use. Yeah, we'll do it next time. For Watkin, without this matrix inverse, we'll see F bar of theta is continuous and nice, and so you can apply the ODE method really nicely. You know. Actually, one other hack that's popular, I don't know why. I think it's because they're scared of the continuity issue I'm talking about. Number 3 is to take, for lambda equals 0, is the only place I've seen it, is you look at 1 over n plus 1 g n plus 1 And I'm just tired of writing out the whole thing. By psi t, I mean psi evaluated x to ut. I'm just tired of writing that down. So that's a little less scary than trying to invert A, because A is not positive, definite. It's not. Did I lose a sign somewhere? Fuck. Everybody minus sign. G star is minus A inverse, minus A inverse. A is like a negative thing. I got to put a minus sign in front. But this thing here is nice and, you know, not going to cause any problems. And so that a whole bunch of people call this the Kalman filter without any justification. They use this and they call it the Kalman filter. It's not. It's not. There's no mathematical. There's no reason for using that. But in I don't know, the one example we've looked at, it did a good job. You know, not perfect, but it did a good job. Yeah.
Why does lambda have to be 0 for that?
Well, if I didn't have 0, the thing I'd end up with I'd have to have my eligibility vector times psi transpose, and then I wouldn't be able to say, hey, it's positive semi-definite.
Oh, I see.
Yeah, but maybe it is actually. Come to think of it, it just occurred to me. I think I might be able to prove that's a positive matrix. Not positive semi-definite, it's not symmetric, but it still acts as a positive. Nobody's done that, but I bet you could. If you, for lambda non-zero, you'd put a zeta t there. I bet it would work. Yeah.
Was there a particular reason you wrote it as G and then G inverse?
Yeah, well, this that I didn't want to have to.
Why not define that as G and that as G?
It's notation with research with Aditya that that we've been using G for matrix gain. So I had a little G. I had a GN here.
Okay.
And so for a matrix, we'll just use it uppercase. That was the reason. G for gain. Yeah. All right.
Okay.
And that might be the safest for you all. I know with a little rover is to use a matrix gain. Start off with just try that out. But you're still going to need a constant. Oh yeah, that's right. What the hell? No. That's not what they do. Times some scalar. And you're going to have to figure out what the hell you could use there if that was true. Yeah. The example I'm thinking of, they had to take trial and error and they took G equals 100 or something. Yeah. No, that's the thing is that, I don't know. I mean, what's really exciting is that, so Aditya and I have this project together on this. It's just coincidentally. And the example I'm talking about, they, by trial and error, found a G which gave the best performance. And then we went and did a post-mortem and estimated A in this way and did everything. And it turned out their worst eigenvalue was at minus 0.51 or something, or 55, something like that. So what they got through just hacking and playing, and I don't know how many months this poor grad student played until he got G equals 100 or whatever. It turned out to be exactly consistent with the theory, just pushing the eigenvalues so that they were just outside of this boundary. It's really fun to see that. Yeah.
They know the theory.
They didn't know. The thing is that one of the authors did know the theory. That's what I mean. I don't get it. One of the authors knew the theory perfectly, but they never referred to the theory. And I think that people just don't realize it's applicable. I think they don't realize that you can apply the theory even for a Markov chain. See, that often when you read the literature, the phi n is assumed IID. And instead we have a phi n which is a big Markov chain. And I think it's possible that people don't realize you can apply the theory in a Markovian case, but you can. It's just, there's no problem. And the theory, it's hard to prove things, but it's really interesting. There's a strange disconnect in the literature, Yeah, so where are we? 3:19. We have lots of time. But we should take a break, right? I mean, some of you are fading. Yeah, let's take a short break and just 5 minutes or something. And maybe somewhere in between. So somewhere in there. And it's very, very. It goes to infinity there, and then it's very flat here, and it's
I was just thinking something related to the reciprocal. So as we get closer to 0, I get farther. So I just picked up.
Yeah, no, 4 would probably be a good choice. Yeah. All right. There's so many things. So in terms of design, what else should we say? There's some other things to talk about. Any other questions before I? Let's see.
Is there a way to I don't know, get a feel for how much, if all of these are tools to attempt and try, looking at the rover problem, which is deceptively not simple, I'm still not sure.
Yeah. Well, it's simple based on the fact that the process lives in a very small space, and we're only trying to approximate the Q process where it actually lives. But you better make sure you really are exploring enough. It may be that the effective state space of this process is almost finite. It's like if you explore like mad, you still only see a few dozen points. And you really only need to know the Q function on those points.
So, basically what I'm trying to ask is how much of these, we wouldn't want to call them hacks, but how much of these hacks are we going to need to get this to work?
Yeah, well, you definitely, the most important thing, I mean, I think you're probably going to have to do this. I mean, you know, to really be sure, you probably will have to estimate A. And you can see it's not hard. There's a, averaging this is not a big deal. And you'll probably, for those of you who have trouble, you'll probably find this has eigenvalues that are very, very small. You know? And you can imagine you squaring a belief state, and it's going to have small entries, you know. And so, you know, it's possible that you have to crank up the gain. And then whether you want to do something like this, or do this times a constant, you know, any of those things will work, you know. The best one, I don't know. But if you don't, if the eigenvalues don't get shoved over it, you can have a lot of trouble, you know. And that's why, of course, I never ever intended this homework assignment to be due today. I knew I was going to, you know, take some time to. You'd have to fool with it a bit and then play some more. Yeah. One more hack. So, I mean, this is about this G thing. So, I want theta to converge to something uniquely. I better make sure I need linearly independent . Now, you can say, well, like in the example, suggestion I gave you for the Grover problem, you say, oh, well, God, they're quadratic functions. They're linearly independent. But u squared and u are the same thing if you define u to be 0, 1. If u only takes on value 0, 1, u squared and u are the same thing. so u squared and u, so it wouldn't be linearly independent if I had both u squared and u as basis functions, you know. And, you know, yeah, so this is, right, these are the entries of functions psi 1, psi 2, psi 3. So I suggest to take them all quadratics. And so to formalize this more generally is what you do is you say, I look at it in steady state of the steady state expectation of that, and I'll write it out. Let's give it a name. Well, let's call it G inverse. It better be invertible. Yeah. So this thing would converge. Oh, no, I can't call it that. It has a little G in it. Bad notation. Let's just call it M.
Just move the little G over to.
Yeah. Forget it. Let's just because capital G is supposed to be a matrix gain. Let's stick it all there. By linearly independent definition, that's, you know, full rank. So let's put a definition there. Okay. And so you can do something with this too, another hack as well. So what happens in practice is often you'll find it's almost rank deficient, you know. So what you can do in practice is you can prune your basis. So, I mean, if this thing is rank deficient, you can prune your basis, as I will describe. But even if it's not rank deficient, it might be incredibly singular. It might be that some of the eigenvalues of this are really close to 0, and you could think that maybe those those parts of the basis, there's some parts of the basis that don't matter. So this is something that people do, and it's a weakness in my understanding. Whether or not how justifiable this is, let me just present it to you as another hack. All right. So this is the last hack, which I think would be fun to play with if you've got nothing better to do. So you can estimate m like that. I mean, you have an estimate of m. All right, so as n goes to infinity, that's just converging m inverse, and then there's a scalar here which is fixed. You can find the eigenvalues of m sorry, using the same name. Should I use a different symbol? Let's call them gammas. How's that? Just to make sure we're not... I didn't use beta. I was really careful not to use beta, just to make sure we don't confuse them with the lambdas that are here. All right, these guys are non-negative, right? You know, and let's suppose I've ordered them. You know, I mean, let's order them the other direction. So I've ordered them for positive semi. This is always a positive semi-definite matrix. Its eigenvalues are real, non-negative. It's possible that the last ones are 0. That's the case where this fails, right? Okay, but you can estimate this on the fly, and what people do, and there's eigenvectors. Is they basically change their basis on the fly. You know, just pick out the top m eigenvalues. Take an integer m less than or equal to d and define a new basis. And psi k is going to be equal to, put a bar in front of it because it's a new basis, will be vk dotted with psi. Because psi is a column vector of functions of height, d-dimensional. Vk are d-dimensional vectors because they're eigenvectors of m. All right, so I can take a dot product and get a new function. That's a function of x and u. All right, and yeah, and basically throw away the guys who you think are not important. All right. Yeah. So if this is rank deficient, you've got to do this. Okay, I mean this is it. So basically, if the m had rank, specialization. If the rank of m equals d minus m, then damn it, do that. I mean, that's the thing to do. your new m will be full rank. Yep.
What is little m?
Oh, you just pick it. You say, hey, that's 25, 23, 18, 6, 0.1, 0.01. Just throw one the ones that are small. And you say, well, it's almost m-dimensional, and you throw this away. I don't know. I get nervous now. At these points like this, I guess feel like I'm on the edge of a cliff because it really is sensible to do this. In fact, in this case, you have to do it. The theory won't work. Nothing will work. You've got to change your basis. This is a way to do it. The new basis will have an m which is full rank. But the thing is that the Galerkin approach was based. You've now reduced the size of the problem. The size now are now instead of how do I say this? I'm sorry, the vector psi bar is in Rm, and so you have less test functions in this Galerkin hack. That makes me nervous.
It's starting to really seem like POD because you're,
Yeah,
it's like the dimensionality.
that's what it is, yeah.
Because you do the same thing, you
Yeah.
throw in small eigenvectors. And
It's, yeah, POD, yeah. So the last hack was POD, principal orthogonal decomposition. Is exactly that. It's just that it doesn't quite, it's not, I can't feel total confidence because of the fact that I have those test functions now that were, I had D constraints in my Galerkin relaxation, and now I have M constraints in my Galerkin relaxation, and that just makes me nervous. All right? So I can't have total confidence that throwing away really tiny eigenvalues isn't going to cause some trouble somehow. You know? So it's and maybe there's some literature I'm missing. I mean, maybe there's a gap in my knowledge that justifies always doing this in this context. You know, of course, there's lots of cases where where this makes sense, but in this context, it's not totally clear.
So the subscript k there is different from n. That's an iteration.
No, K, that's for each K. So, you know, sorry if I didn't. Sorry.
Going through the eigenvectors.
So yeah, you take the first. You take your first biggest, M eigenvalues, and you look at the projection onto that eigenspace, and you take that to be a new place for approximation. It's perfectly legitimate if we were just talking about real projection of that space, but we're talking about some weird Galerkin relaxation of something else, and so there's some danger that that you might want to throw in some new functions. You might want to do this, but then increase the dimension again by just throwing in some other new functions. And that's actually what you'll find people talk about, is you'll prune and then pull in some new crazy functions, new features, and actually do that on the fly. Right?
So,
yeah.
So that psi bar k, that gives you the first element of your new psi.
Yeah, so the new psi bar is an m-dimensional vector.
And so you're able, because you know psi, the original psi analytically, as you showed it.
Yeah.
You then know psi bar k analytically.
Yeah, well, you basically, you're going to go and perform this thing, and you can get like this rover problem. It's so fastly ergodic. I mean, this estimate of m will converge really fast. I mean, that is you start with a 3-state Markov chain. You've got this belief state that regenerates every time y equals 1. It's a completely forgets the past. It does it very frequently. So it's a very fast mixing Markov chain. So you can get a good estimate of m by doing this for moderate sized m, and then do this. And I'm really curious about what you'll get for the quadratic case. I'll bet it'll be rank 3 basically or something. I bet it'll be very small.
So if we were to do this, so we would run the Q-learning algorithm for some amount of time, say 1,000 or 1,000,000 or something.
Yeah.
Get our m, and then we would compute this new basis vector and then start over.
Well, you wouldn't even have to apply Q-learning because you could just go and estimate this based on 1,000 samples for just a few thousand samples.
Size just depend on x.
Yeah, if psi only depends on x. Yeah.
And
X and U.
U can just be a.
And yeah, you choose U to be some randomized policy. I shouldn't be so flippant. I mean, depending on the model, you might have to make n very large. This particular example is very quickly mixing. So, 10,000, that'll work great. Yeah.
And so then once you have your m and do your b's and everything, then you get your new psi bar, and then you can apply it.
Then you just let the Q-learning algorithm run with this new basis. Yeah. I don't know. It's again. I have the least of all the hacks we talked about. I have the least confidence that I don't know the range where this will be useful or not. But it's something that people always are doing, so you should know about it. Okay. Let's see. Wow. Man. We covered a lot of ground. So I have a to-do list here, and I thought there's no way we'll cover all this in an hour and a half, whatever, and we basically have. And not only that, I gave you a hint at stochastic